David Smith here with another Flip Classroom math video. A few tips before we start. Remember that you can slow down or speed up the playback if that helps you follow along. You can also pause the video at any point to catch up with your notes or to try the problems before I explain them. Finally, you could turn on the captions and read my words below on the bottom of your screen. Okay, let's do part 2 of our little series on linear modeling. So before we get into that, we need to do a little bit of background. You probably did this before, but this will be a little quick review of the idea in a very simple problem. So finding the intersection of two lines. Now this will come into play in the word problems that we're going to do, but right now we're just going to do it just with the math. So I have two functions. F of x is 2x minus 1, and g of x is negative 3x plus 4. Now I'm going to go ahead and graph these and we'll see where they intersect. 2x minus 1. Y-intercept is negative 1, so that's right down there. And the slope is 2. That's rise over run, so it goes up 2 and over 1. So that would put it right there. And this would be our line. Properly labeled, f of x equals 2x minus 1. Okay, now let's do our second line. The y-intercept is positive 4. That's up here. And then our slope is minus 3. So we go minus 3 down and over 1. 1, 2, 3 down over 1. So it's going to go through right this same point. And there's our second line. And this is g of x equals negative 3x plus 4. Now these are two separate functions, okay? They're linear, they make straight lines, but they intersect right at this one point, which is the point 1, 1. Now I want you to pause the video and think about what that means. This point is interesting with respect to these two functions. Why might that be the case? Okay, if you thought, well, that point satisfies both equations, you're right. Graphically, it's obvious. That point is on both lines, so that point satisfies both equations. Now, if you put in 1 in here, you're going to get 1 out, and if you put in 1 here, you're also going to get 1 out. So that shows you that the point 1, 1 satisfies both these equations in the same way, and that's where they intersect. So we have one point that works for both functions. So all the functions that you're going to get in the word problems aren't going to be as clean and neat as this one. Plus, throwing up a graph like that takes a little while, and if the functions are more complicated and the units are kind of weird, you spend a lot of time graphing. Now fortunately, your fancy schmancy calculator, the TI Inspire, will do this for you. You can key these functions in to the calculator, and then when you get the graph, you can actually use the tool to figure out exactly what that point is, and it will tell you exactly the coordinates of that intersection, which is also called the equilibrium. Okay, I realized later that there's another way to solve this one that I want to show you right here. So just a minute ago, we solved it by graphing these two equations and finding out where they intersected. And that was the equilibrium point, the point that satisfied both equations. And that worked pretty good. On the graph, I did a hand graph, but you could also do this on the fancy calculator and it would show you that point. We can also do this algebraically. It's actually fairly straightforward. You just have to do one critical thinking step. So the point that solves both of these equations means that they're equal to each other, okay? So if we set f of x equal to g of x, then we can solve for x algebraically and we can find the point we need to find. So watch this. 2x minus 1 equals negative 3x plus 4. I'm just setting f of x equal to g of x. That's that intersection point on the graph where that one point satisfies both equations. It means that they're equal. So I can set the two functions equal to each other and then solve for x. So here we go. I set the functions equal to each other. Now I'm just going to solve this equation. I'm going to add 3x to both sides. and get 5x minus 1 equals 4. Add 1 to both sides and get 5x equals 5. That gives me x equals 1. So that's the first coordinate point. And remember, that was our first coordinate point on the graph. Now what we do to find the second point, we just take the 1 and we put it into either equation. So I'm going to go ahead and use f of x. So f of 1 can be 2 times 1 minus 1, which does equal 1. So our intersection point is 1, 1. Now your calculator can do this for you, and that's great, but pay attention to instructions on tests and quizzes, because if it says find that intersection point algebraically, you're going to need to use a technique like this. Okay, let's do an example. This is something that you actually might need to decide in your adult life. Let's say you flew somewhere for a conference and you've got to rent a car to get around town while you're there for your conference. So in this case, you're given two options for renting your car. Option A, $4 per mile. Every mile you drive, you pay $4. Option B, you have an upfront cost of $100, and then after that, it's $2.50 per mile. So right now, I want you to pause the video and tell me which one you think is the better deal. Okay, if your answer was, that depends, you're right. It depends on how many miles you drive. If you don't drive very many miles, this one might be better. If you drive a ton of miles, this one might be better. So you have to do a little math to figure this out. Okay, so let's do two questions to get started. First question, find the cost for 100 miles for each car. Okay, so pause the video and do that. Use this information and figure out how much it costs to rent each car for 100 miles. Okay, let's see how you did. Option A is just $4 times 100 miles is $400. Option B is $100, that upfront cost, plus 100 times $250, which totals out to $350. So if you know you're going 100 miles, obviously option B is going to be cheaper. Pause the video for a minute and write the formula for each function. Each of these rules for how much it costs to rent a car can be viewed as a function. For bonus points, try to write it in function notation. Okay, let's see how you did. I'm using the letters here for our rules as we got them first. So A of m, which is the cost as a function of miles, is going to be 4 times m. That's the $4 times the number of miles. Pretty simple function. Second one is only a little bit more complicated. That would be B for this rule. B of m is 2.5 times the number of miles. That's this part here, $2.50 per mile, plus the 100 upfront cost that you just pay to rent the car. Okay, now let's take a more interesting question. When are the costs the same? And this when would be what? Think about that. What are we asking for? We're asking at what mileage are the costs the same. So this when is really a miles question. We're trying to find the miles where the costs are the same. Now before I turn you loose to give this a shot, I wanted to let you know I put our formulas here for our functions. A of m is just 4m, that's $4 per mile. B of m is 2.5 per mile plus $100. My phone's ringing. Sorry for the interruption. Let's continue. So we're trying to find out when, in terms of miles, are the two costs the same. And this requires a critical thinking leap to figure out how to do this. We're going to attack it algebraically this time. So think about this. We have two equations. Here is the cost as a function of miles for option A, and here is a cost as a function of miles for option B. Now there's a way to use both those equations at the same time and find the miles where the costs are the same. So pause the video and think about that. Okay, so here's the leap. When the costs are the same, these two things are the same. It'll be the miles that make this the same as the miles that make this the same. So all we have to do is set this part equal to that part. So we're going to write this equation. 4m equals 2.5m plus 100. So this is the cost for option B. This is the cost for option A. We set these two costs equal to each other because that's what we're looking for. We're looking for when is the cost the same, and we're going to solve for miles. So it's pretty straightforward now. We're just doing a little bit of linear equation solving, so pause the video and find m. Okay, let's see how you did. My technique here is going to be to subtract 2.5m from both sides. From 4.5, that gets us 1.5m equals 100. Divide through by 1.5, and we get, that becomes 66.7 miles. It's actually 66.66 repeating, which is 2/3, but we're going to round that up to 0.7. Now, if we wanted to check that, we would just put 66.7 into this equation and make sure that our cost was the same as when we put 66.7 in this equation, and we'd find out that that was correct. Okay, as a formality, let's find out where that cost is. So I'm going to take my 66.7 and I'm going to plug it into this equation. It's a little more simple. So this would be A as a function of m equals 4 times 66.7. So that comes to $267. Now, let's do one more thing. So I added an E part to this problem. Show this graphically. So go ahead and pause the video and sketch, you don't have to plot points, but sketch a graph that shows what we found out here in C and D. Okay, so I plotted my line for A, that's option A. It has a slope of 4, because this is y equals mx plus b, we have no b. And then my option B is this line, this more gradual line, and where they intersect is 66.7 miles and $267. So if I asked you to show this graphically to make a sketch, that would do it. Now that you've finished, write down any questions so you can bring them to our next class and get some help. Remember that you can always watch the video again to improve your understanding. If you enjoyed it, please click the like button down below, and if you'd like to help me grow my YouTube channel, please click subscribe.